Hi, for those of you already on the line, we'll be waiting just another couple of minutes before we get started. Thank you. Right, so that's on top of the hour, so let's go ahead and get started. Hello, everyone. My name is Julia Matevosyan. I'm an associate director and chief engineer with ESIG. ESIG serves in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors across the globe to catalyze rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated, holistic approach to the necessary knowledge, education, and support to power system operators across 5 action pillars. At the core of GPST is a large cross-section of system operators from around the world who are dealing with a rapid transition from a system based on synchronous machines to one built around inverter-based resources. The 5 pillars of the consortium include research and peer learning pillar, technical support pillar, workforce development pillar, standardization pillar, and open data and tools pillar. ESIG is a co-lead of Pillar 1, which is on research agenda, and we are doing it along with Mark O'Malley of Imperial College. More information on GPST can be found on www.globalpst.org. As the co-lead of Pillar 1, ESIG would like to welcome you to this January monthly webinar of our joint GPST Pillar 1 ESIG webinar series. This series is in addition to regular ESIG monthly webinar series, and it focuses on GPST research agenda and associated topics being addressed by Pillar 1. Topics are presented by both system operators as well as members of industry and the research community. An additional series of webinars for other 4 pillars of GPST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about GPST and how to engage, please go to www.globalpst.org, click on Get Involved tab, and further information on ESIG can be found at www.esig.energy. Next, I would like to cover a few logistical matters before we get started. So the lines will be muted for the duration of the webinar to avoid unnecessary distraction. For Q&A, we'll use Slido platform at slido.com. To ask question, please navigate to slido.com, enter ESIG, ESIG 22 as an event code. The instructions are also at the bottom of the screen right now. You'll see a thumbs up button next to the question on Slido to allow you to cast your vote and help us prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap up at the top of the hour. An email and a link will be provided once the video file has been posted. We also plan to provide short responses to all unanswered questions after the webinar, so please don't be afraid to ask your question using Slido. So today's topic is dynamic modeling and analysis of contemporary power systems. As you all know, power systems are undergoing rapid change with uptake of inverter-based resources such as wind, solar, and storage, as well as change in demand characteristics. Study methods and tools have also significantly evolved since classical books on dynamic modeling and analysis were published. I think sometimes in August 2021, we started working on the CIGRE Green Book on power system dynamics modeling and analysis in evolving networks to capture recent changes in this area. It took about 3 years and a lot of hard work from many experts who contributed to the book, and the book got published in August 2024. So this webinar will present a summary of all chapters of this ESIG Green Book on power system dynamics modeling and analysis in evolving networks. It will be presented by Babak Badrzadeh, who is currently Managing Director of Etik Energy, a consultancy business based in Melbourne, Australia. He has more than 20 years of multi-sector power industry experience, including positions at AEMO, Vestas, Ericon, and Mott MacDonald. He has provided consultancy services to many national and international organizations and investigated a wide range of practical power system phenomena. His contributions to international organizations include successful completion of 3 CIGRE technical brochures as a convener, an ongoing associate editor of IEEE Power and Energy Society Power and Energy Magazine, and distinguished lecturer of IEEE PES. Babak is a fellow of engineers in Australia, an adjunct professor at Monash University, a recipient of ESIG Excellence Award, and convener of CIGRE Australia C4 panel on power system technical performance. He will be co-presenting with Zia Emin, who is a technical executive with Electric Power Research Institute, EPRI. He has extensive knowledge in all aspects of power systems modeling, including steady state, frequency, time domain modeling, and substantial experience in harmonic performance specifications for power electronic interface devices. Prior to joining EPRI, he worked as a power system engineer specializing in planning and development of electric power networks, initially with National Grid and later with WSP and PSC consulting companies. He has been active in many CIGRE working groups as a member and convener. He received CIGRE Technical Committee Award in 2013 and Distinguished Member Award in 2014. From 2016 to 2022, he was a chairman of CIGRE Study Committee C4 and its Strategic Advisory Group. He was also a member of CIGRE Technical Council at an international level and the past chair of national level CIGRE UK. Currently, he's a member of CIGRE Strategic Advisory Board. Over the years, I come to greatly value and appreciate the work Babak and Zia are doing and the leadership that they are providing to the industry. It was a great honor for me to collaborate with them over the course of these 3 years on the CIGRE Green Book as well. All right, so just a short reminder, use Slido at slido.com with the event code ESIG22 to ask your questions. And with that, let's go ahead and get started. Zia, I turn it over to you.
Thank you, Julia. Thank you very much for that introduction. Okay, I have the control, I believe. So let me really start by thanking ESIG for giving us this opportunity to provide a summary of this Green Book, with the aim, of course, of reaching wider people in the industry. I'll kick off the presentation and provide an overview of the book, touching really at key coverage of each chapter, and then hand to Babak, who will have a deeper dive, I think, to some chapters, followed by a selection of topics from various chapters, and covering all would be impossible almost within the given time slot. So I need to master this. Okay, key highlights about the Green Book. It's the 14th in series, I think the 16th to date within CIGRE. It's a major reference book, meaning that it can be updated online, I believe, as part of the definition from the publisher. It's a first for Study Committee C4 in CIGRE. As you might know, Study Committee C4 has a very wide remit, and therefore it's very, very difficult to concentrate on one and find sort of volunteers to go for this. Babak was one of them, so thank you, Babak. The book is about 900 pages, and it was delivered well before the planned date. The other sort of interesting thing about the book, it has 50 plus authors from 11 different countries. Now, just to give you a feel and thank those people, here are to prove the point effectively. You may recognize some of these names or all of them, but it is suffice to say that these are the real heroes, really, who made the book a reality. So a big thank you to all of them once more on behalf of the electric power industry, I would say. In terms of managing the book and the flow of information with so many authors and to make it all easier for ourselves, really, and partly maybe due to the publisher recommendation, the book is divided into 7 parts led by Babak, myself, Marta, who is the current chair of C4, Julia, David, Nilesh, and Deepak. And all of us really, when we were sort of going through these chapters, were looked after by the most capable Genevieve. I can't sort of ignore Genevieve there on the side, who was at the time when we started this and is continuing to be the case really as secretary of Study Committee C4. So a big thank you to her really for keeping all of us in the straight while we were working on this book. Okay, next one. The fun part, managing those sort of 8 people among us having meetings, I think it was probably the most difficult thing to organize because 3 of us on one side, the other 3 on the other side, and myself and Marta right in the middle. And we always drew the short straw, myself and Marta. So most of the meetings happening at the European late night time, but we are not complaining. It was an excellent collaboration. So again, thank you to all of those who collaborated. Now, in terms of chapters, the first chapter, it discusses really the evolving dynamics and stability challenges in power systems. And this is due to the increasing penetration of inverter-based resources, emphasizing the need for advanced modeling and simulation tools to ensure secure and reliable power system planning and operation. I'm not going into the details of chapter 1, which will become, I think, clear in a minute when Babak starts presenting. So chapter 2, it follows on from 1 in terms of subject and discusses the various stability challenges and considerations really in power systems with high penetration of power electronic interface devices, emphasizing the need for appropriate analysis tools and methods to address voltage, angular, frequency, converter-driven stability issues, and also the interplay between power quality and system stability. Now, Babak is planning to go a little bit deeper for chapter 1 and 2, so I won't spoil it and leave it at that, which will become clearer, I think, a little bit later. Now, the third part, which is the longest part of the book, it has 5 chapters. Chapter 3 discusses the principles and strengths and limitations of phasor-domain transients and electromagnetic transient simulation software programs, emphasizing the complementary roles in power system dynamic analysis and the importance of selecting the appropriate tool for accurate stability assessments in modern power systems with high penetration of IBRs. It also explores the increasing importance, I think, of EMT simulations in modern power systems with high penetration of IBRs and the potential benefit also of co-simulation techniques combining phasor domain and electromagnetic time domain. Chapter 4 highlights the increasing importance of EMT simulations over phasor domain for wide area power system studies, especially under low system strength condition, again with high penetration of IBRs. It presents really practical examples where EMT simulations accurately, I think, capture the dynamic behavior and stability issues that phasor-domain simulations maybe could not at the time, emphasizing the need for detailed and accurate models. The complementary use of these both simulation methods, both phasor-domain and EMT, is recommended here to ensure a comprehensive sort of stability assessment and effective mitigation strategies in modern power systems. Moving to Chapter 5 outlines various sort of screening methods really to assess system strength and stability risk in power systems, again with high penetration obviously of IBRs. But it emphasizes on top of that the importance of combining different methods to accurately identify potential issues and the need for detailed analysis to ensure reliable and stable power system operation. 6 discusses various sort of linear analysis methods. Maybe it's the dreaded part, it's small signal stability, including eigenvalue-based and frequency domain methods to assess small signal stability in power systems with, again, high penetration of IBRs. Emphasizing the importance here of these methods in understanding and mitigating potential instability phenomena. And lastly, Chapter 7 in Part 3 discusses the need for advanced operational decision support tools in real-time and near real-time power system operations to manage the challenges posed by energy transition, including, for example, high volatility, reduced system strength, and the new oscillatory phenomena. Moving on to 4, which is all about models, and it was the baby of Julia. Chapter 8 provides an in-depth overview of the considerations, challenges, and evolution in dynamic modeling of synchronous machines and IBRs, emphasizing, of course, the need for accurate and detailed models to ensure a reliable operation of power system. 9 provides a comprehensive overview of HVDC link models and detailing their types, applications, and control strategies for operational and planning system dynamic studies. Chapter 10, it goes and discusses the importance of accurate load and distributed energy resource modeling for wide area power system dynamic performance, and it highlights various modeling techniques and considerations for both aggregated and detailed modeling studies. And the final chapter, Chapter 11, it outlines approaches for transmission network modeling in EMT dynamic studies, emphasizing the importance of accurate network representation and the integration, crucially, of the protection systems to ensure reliable power system analysis. Moving on to 5, which is solely dedicated to studies. It has 3 chapters where 12 outlines the procedures and requirements for grid interconnection studies. This is the connection to the grid of IBR and HVDC type of projects, emphasizing the importance of compliance with evolving grid codes and the use of detailed phasor-domain and EMT models. It provides some practical examples, which includes, I think, cases of wind plant interconnection in Australia and HVDC interconnection study in Manitoba, highlighting the need for comprehensive analysis to ensure reliable and stable operation, of course, integration of these technologies into the power system. 13 discusses methodologies for planning and operational of the power system with high IBR penetration, primarily focusing on interactions, oscillations, system strength, and inertia, again, to ensure stability and reliability. And the final chapter within Part 5 explores the impact of DER, distributed energy resources, microgrids, and industrial power systems, and network protection systems on the dynamic performance of wide area power systems. Again, the emphasis is on the need for specialized interconnection, planning, and protection system design to ensure stability and reliability. Moving to 6, which is about model accuracy. It has 2 chapters. 15 outlines the importance of model acceptance testing in power system analysis, again, concentrating on the need for robust and accurate models to ensure reliable performance under various operating conditions. It details, chapter 15, methodologies and tests required to validate the adequacy, the numerical robustness, for example, and performance of both plant and system-wide models, including specific tests for phasor-domain transients and EMT models, as well as grid-forming inverters. 16 emphasizes the importance of validating power system plant and network dynamic models to ensure reliability and security in power system operations. It outlines various validation approaches, including, for example, playback, wide area integration, hardware in the loop, and model certification, providing practical examples to demonstrate the methods I just spoke about. The last part of the book, again, 2 chapters, it's moving into the artificial intelligence domain. Chapter 17, it discusses the application of computational intelligence, really, and machine learning techniques to enhance power system dynamic modeling, analysis, and control, addressing the challenges, for example, posed by the increasing complexity and uncertainty in modern power systems. It specifically highlights the potential of cloud-enabled scalable computing, artificial intelligence, and probabilistic models to improve the accuracy, efficiency, and reliability of power system simulations and predictions, particularly in the context of high penetration of DER. And finally, 18 discusses the importance of using probabilistic analysis, optimization techniques, and standardization to improve power system dynamic analysis, particularly in the context of increasing the variability and uncertainty due to high penetration of IBR. It concentrates on the need for advanced tools, data interoperability, and collaboration among stakeholders to ensure reliable and efficient power system planning and operations. So in a nutshell, those are the very high-level overview of the chapters, and I will now hand over to Babak to take us through some detailed discussions. Babak?
Thank you, Zia. Okay, so what I will do for, let's say, next 30 minutes is to provide a little bit more detail on some of the topics that Zia mentioned, and then bring everything together to make sure that they all part of a coherent story, what we're trying to achieve and what tools we are trying to provide to the industry. I will start with part 1, which sets the scene for many of the things that we then decided to do for the remaining parts or remaining chapters. So starting from the reasons that we started to develop this book, Julia already mentioned briefly in her introduction. I will provide a little bit more detail. So this was obviously important for us to make sure we are focusing on things that will add value. We are not repeating things that are already understood. And at the same time, once we come back and finish the book, we make sure that everything that we had in mind as summarized here in this slide will be covered. One that already mentioned is that the generation mix and the types and the power system is changing, whereas most of the classic books have been focused and still remain excellent readings for synchronous generations, but there are not much coverage, if any, of new and emerging technologies based on inverter-based resources. And not just that is not covered, but even if you look at more broadly, not just the classic books, the emergence of new technologies, whether they are grid-forming inverters or data centers or many other concepts that are not very well understood in terms of performance and importantly in terms of how they need to be modeled. And then we're talking about larger scale generation, but we can't ignore the increasing penetration of power electronic based loads and power electronic based distributed energy resources and how they could impact the larger scale system stability, which we have discussed in the book. And then if we look at what are the main pillars of the power system, we talk about generation technologies and grid following, grid forming inverters and loads and DER, but we can't ignore the network itself. It's not a bunch of lines and transformers, etc. It does interact, and we have demonstrated examples and case studies to make sure that the impact of transmission and even distribution networks on bulk power system stability is modeled and understood, and what are different types of models that we can use, as I will explain a little bit later. And then the interactions between tools and phenomena. Again, I will elaborate this later, but in short, what I mean here is that previously it has been appropriate for an engineer to use a tool for an application and to reach a very high level of certainty to make sure that the results are not dependent on something else that needs to be done on another simulation platform, for example, because in one we will do power quality studies and in the other one system stability, and the two could be treated fairly independently without loss of accuracy, whereas that paradigm has moved, and I will discuss that in more detail, and how we can recognize and capture this interaction and include it in our power system modeling and analysis. And last but not least is that many of the tools that we have been using historically, again with good confidence and high accuracy, may not be accurate or may not be able to simulate some of the new and emerging phenomena and emerging complexities, which I will explain in the next few slides. So what these phenomena are, what I have done or we have done in this slide is that looking at the power system phenomena more broadly, obviously as the name of this Green Book entails, our focus was our power system dynamics and stability. But here it was important to recognize what are the broad range of power system phenomena, which they have been divided into three categories here. The first, which is our focus, system stability, and then power system harmonics and high frequency transients. The importance of this table is that to set the scene as to what we are focusing, and equally importantly, what we want to be focusing, and then educate us what are the phenomena within the subset of system stability that we can confidently model, and what are the factors that influence this, and then if there is an instability, how we can break the causation chain, which I will explain in the next few slides. Important takeaway from this slide, and I won't be going through each cell here, is that it's as a rule of thumb, we can consider the typical frequency range of system stability phenomena up to 300 Hertz. And a big part of it is that it is consistent with the typical bandwidth of the control systems that used in inverter-based resources, meaning that any phenomena up to this frequency, you can expect that with changes within the control system, you can positively or negatively impact the system stability as indicated in the overall impact column. Moving on, now, as I mentioned in the previous slide, we decided that we will be focusing on the system stability. There will be interaction with harmonics, which I will explain a little bit in more detail, but that is only up to relatively lower order harmonics, and we will be leaving high frequency transients completely out. Now that we decided what we want to focus on, and we have discussed different forms of system stability, which I will take you through a little bit in more detail. I'm not explaining which is which. There has been plenty of great work has been done in the industry, including by IEEE in this revision of the original classification that was done in 1994. We have discussed this briefly, and we haven't decided to make changes at this high level. We have some modification that I will discuss with you, but the intent of this color coding is different. We have kept exactly as it was as per the IEEE terminology. We decided to use color coding to determine interrelationship between system stability, which is a widely used term, and then a more emerging term that has been discussed multiple times in the book, and because it is a term, a challenge that pertains to many power systems around the world, especially those that experience high share of inverter-based resources, and that is system strength. And it is not fair or accurate to relate system strength only to one form of stability. What we have done here as to what are the different types of system stability as per IEEE definition that would be most strongly or least strongly related to the system stability and system strength. Okay, now looking at the simulation tools, there has been several hundred pages of focus of different simulations, but looking at it a little bit in a bigger picture, and here what we are showing are different simulation tools that are used for planning and operating a power system. It doesn't necessarily mean that all tools are those we as power system engineer use. For example, market modeling or climate events modeling, and hence the color coding here, which is intentional. So what we are showing here is that the green colors are showing the types of tools that currently used in a power system to analyze system dynamics, ignore other phenomena that we already ruled out. And then the interrelationship and intersection between the circles is intentional as to there, for example, could be input-output relationship or concurrent use of two tools in order to get a more confident answer. And this is not necessarily the size of the circles is not to suggest that they are more prominent users. Still, phasor-domain simulation remains the most widely used tool for analyzing system stability, but these are the relationships. And then you can see, for example, there is a small intersection between the protection and some of the dynamic analysis tools, whereas power quality largely untouched, so there is not much of interaction currently with dynamic analysis. And then this is our view of how it will look like, or it should look like moving forward. And like Sia mentioned already, we have even things like machine learning and AI that is not currently used, at least very widely in the industry, but these are some of the enablers and facilitators for better use of different tools. And unfortunately, the bad news here would be that as much as there is a strong desire for us to use a limited sets of tools, there will be not a single tool that can answer all questions independently, and the interaction between different types of tools. So how they will evolve in order for us to get a collective and confident answer to understand what are the new and emerging forms of system stability and how we can understand and manage them before they happen. Okay, now that we set the scene, looking at it from a different angle. So for the past two slides, we're talking about, let's say, phasor-domain simulation or EMT, or use of machine learning and power quality and protection from a phenomena perspective, but looking at it from a different angle, which kind of brings us to complementary, not similar answer, but a complementary answer, that from a mathematical representation, in the end, all simulation models are mathematical representation of a plant or the power system itself, how it can be divided. And here is a summary of different types of simulation based on the underlying mathematics and assumption, recognizing that the power system that we're discussing is a highly nonlinear system. So it's always nonlinear, and our inverter-based resources equally nonlinear. And we do use these and account for nonlinearity in some of our simulation, like time domain simulation. There are many other different types of simulation, which I will touch on some of it as we go along. For example, there will be an advantage sometimes to be able to linearize this highly nonlinear system for various reasons, for ease of countermeasure development, or understand how sensitivity of different parameters manifest themselves into a system stability. What else is available out there, not to supersede or replace nonlinear modeling, because we cannot omit those nonlinearities, but are there other approaches that will give us some complementary answers? And then talking about the phasor-domain simulation and EMT, what this slide is showing is to consider what are the typical bandwidths of these simulation tools. For most phasor-domain simulations, this is typically around 10 Hz, as is indicated, whereas with EMT simulation, it's down to what level of detail is included. It doesn't necessarily guarantee that an EMT simulation will have a very high bandwidth, but it's down to the modeler as to what level of detail is included. This is important because if you remember from one of the previous slides that we talk about a typical frequency of 300 Hz for system stability phenomena, it means that EMT simulation will not have any challenges in that regard if it is a true representation of actual equipment, whereas there will be some simplification in phasor-domain simulation that in some condition may not be important, whereas in some others may be more important. And how we can make a decision, I will provide high-level factors as we go along. Now, moving to chapter 2, here, after this high-level intro, what we're trying to do here is to discuss each form of system stability to understand what they are, because if we know what they are and what causes them, then we can go and model them, and then we can run studies and develop mitigation measures. So the structure of our thinking is, like I said earlier, what are the causes of each form of instability? What are the contributing factors? What are the consequences or manifestation? And what are the countermeasures? And some of these are very obvious for a synchronous dominated power system. Again, with the spirit of not repeating the great work that has been done for many decades, the focus has been primarily on each form as far as inverter-based resources and high share of IBR in power system is concerned. Providing an example, voltage stability, here are different bubbles, which is really taken from the same IEEE classification, and highlighting that which forms are directly impacted or participated by IBRs, whereas with some others it may be indirect participation. And another point to highlight here is as we are moving to a higher share of inverter-based resources, it will be increasingly more difficult to also be able to neatly and cleanly associate an instability to a certain form. A testament of that is with the short-term voltage instability, there is some participation of converter-driven stability and potentially even transient stability, especially with grid-forming inverters. Now, another topic of coverage, which is of increasing relevance, maybe in different forms in the system, are subsynchronous interactions. This is where we decided to make some changes to classifications that are available in the industry. As you can see, and there are so many jargons that I won't be taking you through, but the main objective is to recognize that what can interact with what other component in the system, and how we can make sure that these interactions are captured. The thing is that these are not necessarily the same thing. The causes are different, and if we don't know the causes, we cannot break the causation chain. Now, I mentioned this topic earlier, and this is still an evolving area. We don't suggest that we have addressed all gaps in the current industry, but recognizing that there are increasing interactions between system stability, power quality, and protection. Like I said, historically, it has been safe. If I am a protection engineer, I look at protection studies. I don't really need to consider power quality. Whereas this paradigm has changed. So in some of our studies, we need to consider the impact of protection if we are interested in system stability. And this is an example of interaction between power quality and system stability. It's a real incident, and we have covered other incidents. This is not the only. What we have learned and how we capture it in terms of system modeling, and then we can understand what were the causes and how we can mitigate such a phenomena from happening. This is an example of a harmonic resonance in a very low system strength condition, meaning high impedance. If you inject even a small current, that would be sufficient for us to create a relatively high voltage, because there is a large impedance. Large impedance multiplied by a small current, it will give you a large voltage. What would happen is that a large voltage would result in the plant to trip because of the protection settings, and the same could apply and will apply in broader systems. So these are not necessarily fast transients. They may be those that last several hundred milliseconds or even sometimes several seconds, but that would be sufficient to trip the plant. And if a plant is tripped, then that becomes a system instability problem. Now, to summarize the phenomena that we have observed, this is a classification of different phenomena, and we don't necessarily suggest that this will cover anything and everything as far as analyzing and learning from experiences is concerned. But we have provided a good summary of all known incidents to the point that we were publishing the book. And these are the 5 categories. Reduced system strength condition, obviously a very clear one. And the interaction with series compensated line, that's the classic. Likewise, interaction with rotating masses of turbine generators, the classical SSR. The 2 more emerging ones are interaction between multiple IBRs, which has been one of our focus, and then recognizing that we're talking about fast controls of inverter-based resources being a key cause of instabilities, but it doesn't mean that the slower controls in inverter-based resources cannot cause instabilities. For example, something like a PPC in a wind farm or solar farm. And these are some of the things that we have reflected in the book. Now, looking at some other topics, and again, this is 900 books in 30-minute presentation, we cannot do the justice, but how we can make it most interesting for 200 or so attendees to brings us to the main intent of the book, which is around power system modeling and how we can improve modeling accuracy to be able to answer some of the emerging challenges. When we talk about higher accuracy, what do we really mean and how we can achieve it? There are multiple ways, at least these 3 ways that we have discussed in different parts of the book. One and obvious is to use more detailed models. The more detailed plant models in particular, IBR, will take us to higher accuracy. And then we don't have a single plant, so we are not talking about microgrids. It's a power system. So if we go highest level of detail with plant model, but the system model is not really detailed or sufficient, then we may not really get what we are looking for. Especially if we're looking at control interaction type of things, we need to represent larger size of the system and more detail in the system. Like I said earlier, the system cannot be considered as a static system. It's not just transformers and lines. There are many other dynamic devices. And then the key is that even if we go with more detailed plant models, we need to make sure that these models are valid, which I will come back to that shortly. Now, these are the some of the aspects that will help us to make a decision on use of phasor domain versus EMT simulation. For example, what is the phenomena that we are looking for? And if we are talking about a phenomena with a dominant frequency of, let's say, 20 Hertz or 200 Hertz, that is a clear indication that we should be using EMT simulation. Whereas a phenomena that is close enough to the system fundamental frequency or a slow enough phenomena, maybe phasor domain simulation is still valid. The other is based on application. If we are using the models to predict system behavior in next 10 or 20 years, how confidently and accurately can we build a system around EMT simulation? Whereas if we're looking at system in next 6 months. And then we're using screening methods, which I will explain in the next few slides, how we can use the screening methods as we discussed in the book to expedite the decision making and the number of cases that we're going to otherwise find. And last but not least, everything is reliant on having data and models and sufficient data and models. And that's the reason why we can't confidently use EMT modeling, for example, to look at a system in next 20 years. Now, the screening methods that I mentioned in the previous slide, this has had a long journey. It has been for 30, 40, or maybe longer, but its use and application has changed and will most likely change. Originally, if we look at the use for IBR, the focus has been, should we be using EMT modeling, for example, as opposed to phasor domain simulation, is still in a single machine infinite bus environment. And then it changed a little bit how we can decide with the use of some screening method whether we should use EMT modeling in a wide area assessment. And then if so, is it only the plant that I am interested, or maybe if we are looking at control interactions, it will be several other devices that could interact and how they could be considered. From a different dimension, historically, the screening methods have been used to educate us the indication of system instability under low system strength condition, and if we need to do EMT studies. It is moving from there because if the need to develop a larger size of a system is required, the important question is how much of system need to be modeled, which I'm referring to vertical and horizontal. And by vertical, we mean how much of downstream system. We're talking about inverter-based loads and inverter-based DR, how much of them need to be modeled and with what level of detail, which we have discussed at great length in one of the chapters. And then we know that we cannot run thousands of EMT studies on a wide area basis. So really what we're trying to achieve, how to use screening methods to reduce the number of studies carried out, but equally importantly, reduce the size of system that is being modeled. Now, looking at, and this is like 90 or so pages, I try to represent everything in one page, that there are so many different types, existing, emerging methods that used as screening methods in power system. There are, for example, some emerging impedance-based methods, which I will touch base again briefly in next couple of minutes. The most widely used are based on fault level and some based on transient stability or voltage sensitivity. And then looking at from a different dimension is that are we trying to look at instability from a small signal sense or a large signal sense, or a short term like several milliseconds or tens of milliseconds or several seconds. So there are horses for courses. And again, unfortunately, same thing that I mentioned on the use of tools themselves. With the screening methods as it pertains currently, there is not one that can be used for all aspects of phenomena and analysis that we are interested. So noting the interactions between controls in particular becoming quite emerging. This is one slide that this is again summary of one full chapter that I'm trying to present in one slide. And you remember we had one slide that we divided different forms of stability from a mathematical representation, not phenomena. This just builds on that. If we are trying to analyze interactions, of course, the first and foremost is EMT studies, but how many studies and how much information do we get to understand what are the causes and how then we can develop mitigation measures. Color coding, again, here is intentional. There are many different methods, but if we try to see how applicable and practical they are for systems with high share of inverter-based resources, some of these like transfer function or participation factor less widely used, whereas the concept of apparent impedance or passivity, which all belong to the family of frequency domain analysis, more widely used, and we have provided several examples in the book. Then considering that more detailed models of system and plant is important, but of course we need to make sure that these models are indeed source of truths. Otherwise, more detail doesn't necessarily imply higher accuracy. And what we're trying to show, again, this is a summary of one full chapter in one slide, that model validation is a journey, it's not a single point in time. There are many different approaches depending on different size of the system, use of different types of tools, and which party or organization can confidently do it. And not necessarily suggesting that everything should be done for all projects or all countries, but this is essentially a journey of model validation from very early stages before even the project incepted. If you know a wind turbine or solar inverter, how you can gain information and validate the model at earlier stage, and then during commissioning, you can validate the model, and then the plant stays connected for another 20, 30 years. How we can use opportunities to validate the model. And last but not the least, this is the very last slide, to bring everything together, also highlighting some of the topics, more contemporary enablers that I haven't discussed. These are really a summary of how all chapters are interrelated. I've tried to write it in as a title, the push for detail and efficiency. So the need for detail doesn't go away. We cannot shy away or try to change that, but the need for efficiency is equally important, because we need to operate systems based on outcomes from this more detailed and a slower simulation, and how we can achieve that. We obviously need enhanced modeling techniques. This has been discussed in 3 or 4 chapters, which has been the only focus of those 3 or 4 chapters, and there are many different types. However, at the same time, when I talk about efficiency, we need to use also advanced computational tools, which we have provided several examples of how people as practicing engineers or research organization use these advanced computational tools. And then collaboration and data sharing, recognizing that obviously more detailed data brings the issue of confidentiality, but the need for collaboration and data sharing doesn't go away, because there is no single side of industry that has answer to all problems, all expertise to investigate and mitigate an instability. And somehow complementary to that is the standardization and interoperability. If we talk about multiple tools are required to provide a comprehensive answer to one problem, not one tool, one problem, multiple tool, one problem, the standardization and interoperability also will be quite important. And then we have around 250 pages of documents, this Green Book, that talks about setting the objectives, processes, and success criteria, because having detailed an accurate model is one thing, but how to use them and how to run studies and define scenario and what the success means, what is stable, what is unstable, this all need to be fleshed out better. And how, as we discussed in one of the latter chapters, to improve decision making and optimization, for example, how to use machine learning and AI to reduce the burden on human on some of the classification or decision making, not to supersede. The screening methods, I've already discussed this in the past slides, to decide how we reduce the size of the system and also how we can reduce the number of studies we carrying out. And needless to say that in the end, all these are reliant on more detailed but more accurate model. And we can only achieve this by validation and testing. This is the last slide in my presentation. Thank you again, ESIG, for giving us this opportunity. I'm happy to take any questions with Zia.
Yeah, Babak, thanks so much for covering the book. It's hard to cover 900 pages in 45 minutes. There are a couple of questions. So the first one is, could you please comment on phasor-domain transient / EMT modeling of large loads, such as data centers, and the impact on stability analysis?
Okay. My new favorite topic that it is. So, okay, so looking at it, and that's really what we're trying to do, because something called wind turbine or HVDC or FACS, it doesn't mean anything, but what is inside it. If you're looking at data centers, and we haven't, by the way, mentioned data center specifically, but I can answer that question. So the framework we have provided is indeed valid for data centers. So if you're looking at data centers, it has DC-DC converters, and it has motor drives, which mostly are inverter connected motor drives, and it could have other power electronics and batteries. So if we had any concern with a battery or solar or wind, all of it exists here. It's not going away. Plus, we're getting something like DC-DC converter, which we even don't know as well as we know DC-AC or AC-DC converter. So maybe the first answer is that do we need to have the same level of detail that we do for a wind or solar? The answer to that is yes, unless we talk about 5 or 10 megawatt data center, which I don't think that's the intent of the question. The second is that what criteria and condition do we need EMT modeling, not just phasor-domain modeling? Again, I would say that anything that we use for a wind or solar or battery, it will be valid here. However, there are two bad news here. So one is that there is no modeling requirement on this type of inverter-based loads anywhere. Many countries are looking at it. I'm personally involved in one country. The second is that there are no performance requirement, and that is even make it further chicken and egg, because modeling requirement and performance requirement go hand in hand. But to summarize, the answer is that it will be very similar to a HVDC or a STATCOM or a wind farm or solar farm. So it is not really any different.
Julia, you're on mute.
Yes, I noticed. Thank you. Well, the next question is, why small signal stability is separated from time domain simulation software packages like Dix Island can do both at the same time?
Okay, you can go.
I don't think the separation is intentional. It's simply because a small signal analysis is not a time domain. It's a linear analysis method as a frequency domain. So it is covered in chapter 6, I think, if I remember correctly, but we haven't really chosen to put them together or separate them based on commercially available tools. So commercially available tools was not really the target here. It was just the analysis domain itself. So covering phasor domain and electromagnetic domain, electromechanical, electromagnetic, and then separate the small signals into a different chapter. It was the logical one. Go on to edit.
So we never mentioned any commercial tools. We recognize that some commercial tools have multiple capabilities. We are not undermining any of that, but these are genuinely two different analysis methods that we wanted to cover.
Sounds good. The next one, what do you think the biggest challenge between one, computing power, two, availability of models and data, and three, having people with required knowledge and ability? What's the biggest challenge?
I think the second one, I think that's part of what we are hoping to achieve, is that people go and read our books, so, you know, and how we can help and work together. You know, I cannot shy away from that problem. Unfortunately, we cannot fix it by the book, but the fact that 50 or so experts in the world, you know, sacrifice their nighttime and weekend time. So one of our, I think we are quite passionate for this to be used by young engineers to bring them up to speed on some of the emerging challenges. And the first one, I think I've already you know, discussed. Everything is a balancing act, is a trade-off. So the capability of computational power has increased significantly compared to even 5 years ago, and that will increase, but it's always going to be a catch-up game, and that's not in our hands. So I think we as power engineers need to make sure we use the latest and greatest in terms of computational trends, but in the end, we cannot run, let's say, I don't know, 1,000 EMT studies to run the power system in every 5 minutes. That's the reality. We can't change that, unfortunately.
And maybe on the last point, the having people with required knowledge and ability capability, Julia, I think in a recent project that came up, and the difficulty of bringing up new generation of engineers to a level to be able to do EMT type dynamic analysis in any software is a difficult one. But one thing that caught my attention at the time was from a few of the utilities, it was far easier to train or retrain classically minded RMS, phasor-domain analytical engineers into the EMT domain rather than just straight into the EMT domain. They will have the necessary background effectively to understand what's going on, and you can train them in a more easier fashion, I think.
Right. Thanks, Zia. We have a couple of questions left. Unfortunately, we won't be able to get to them online, and we have to wrap up at the top of the hour. I want to thank Zia and Babak for really informative webinar on CIGRE Green Book. I think it will serve as a valuable reference for the industry in the future, Zia, just like you said right now. As I mentioned earlier, an email will go out once the video file has been posted, and we will answer the questions that we didn't get to, and we'll get posted the answers as quickly as possible. There was just maybe about 3 questions left. We appreciate your participation, and if you would like to stay engaged, I would like to invite you to participate in the next ESIG webinar on January 30th on short-term congestion mitigation with transmission topology optimization at aligned RNG. Further information on our webinars and events can be found on our website at www.esig.energy under events, and you are invited to attend. Information on all GPST webinars is found at www.globalpst.org. Zia, Babak, I want to thank you once again for this very timely webinar, and thank you all for attendance and your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. See you soon. Bye.
Thank you, Julia. Thank you all.